Okay, we're going to look at a few more statics problems. One thing before we go on, when you are solving a statics problem, you essentially have to make a guess at what direction you think the forces are going. For instance, here in this problem, we have this cantilevered beam sticking out to the right, these two supports A and B, and it looks like someone has guessed that both of these reaction forces will be going up. It's not an unreasonable guess because when you have a load being applied in a downward direction, it's reasonable to assume that the reaction forces are going to be going up. But in this particular case, because the load is being applied to the right here of support B is going to act like a fulcrum. This is going to act like a seesaw. And so we've got the load being applied down here, which is going to make the whole beam want to rotate like this, which means that at support A, it actually has to pull the beam down in order to prevent it from rotating. All that means is that if we had initially assumed the reaction force was up, as apparently was done here, and then we find the missing forces using our three equilibrium equations, that the sum of fx equals 0, the sum of fy equals 0, and the sum of torque equals 0. And what will happen is, using those three equilibrium equations, solving for this, we will get a negative answer. If that's ever the case, if you set up your equation correctly and solve it properly, and yet you still get a negative answer, what that means is that you made an incorrect assumption about the direction. So in this case, the support here at A, that reaction force is not going up, it's going down. The numerical value will still be correct. We just have to essentially flip the sign and say, okay, that's actually going in the downward direction. Let's look at an example problem here. This is a classic statics problem. We have essentially, this actually does act like a truss in a way. We have a hinge support here that supports this horizontal boom, which is then supported with a cable. Now, the nice thing about a cable is we know that cables will always be in tension. A cable cannot transmit a compressive load, so that we know there's going to be a tensile force pulling up on the end of this boom. The thing about a tensile force is that it pulls in towards the center of the member in both directions. So it pulls the bottom of this horizontal boom up, but it's also pulling the wall support to the right. We also have the weight of this sign hanging from the end of the support. We have the boom itself has a weight, mg, and that's acting at its midspan. And then the hinge support is going to have both a horizontal and vertical reaction. It's going to be partially supporting the vertical load applied by this sign. But because this diagonal component of the cable is pulling the end of the boom in, okay, if we look at just the boom and treat it as a free body diagram, it too has to be in a state of equilibrium. So that means that this force to the left must be canceled out with an equal and opposite force to the right. So let's start analyzing this in more detail. The beam length here is 2.20 meters. So I'll just draw that in, 2.20 meters from the support to the end of the beam. Has a mass of 25.0 kilograms. So that's right down here, 25.0 kilograms. is mounted by a small hinge on a wall shown. The beam is held in a horizontal position by a cable that makes an angle theta of 30 degrees. 30.0 degrees to be precise. The beam supports a sign of mass 28.0 kilograms. Suspended from its end. Determine the components of the force FH, so the force in the hinge. The force FH that the hinge exerts on the beam and the tension FT in the supporting cable. So we want to know these two forces. So in order to find these two forces, we first can find their vertical and horizontal components, and then once we know that, we can find the magnitude of the forces. Okay, so let's get started here. So first, we can sum the forces in the y direction. So in the vertical direction, what do we have going on here? We have FHY. We're going to assume that that's going up. So that's our first vertical force is going to be a positive FH, and the vertical component is equal to, well, let's just say, let's call it FHY for now. And what else do we have? We have the mg going down, and the mass is 25 kilograms. So that's going to be down. So negative 25.0 kilograms times g, 9.8 meters per second squared. Okay, that's the second vertical force. We have the vertical component of the tension force. So we've got plus in the upward direction FTY, and that we do know the angle here of this cable, so we can say that this is actually FT. I'll scribble out the Y here, just FT times sine of 30.0. Okay, so we've got that force, we've got that force, we've got that force. The only one remaining then is the weight of the sine on the end. So minus mg, and m is 28.0 kilograms times 9.8 meters per second squared. So this equation alone is not going to solve the problem for us because we still have too many unknowns. We don't know what the vertical force at the hinge is, and we don't know what the tension in the cable is. We've got two unknowns, one equation. So that's not really going to get us to a final answer. But this is not our only equation that we can use. We can simplify this equation a little bit. So for instance, 25 times 9.8 is 245. So we've got, we can make this FHY, positive FHY, minus 245 plus sine of 30 is 1/2. So that becomes plus 0.5 FT minus, and then 28 times 9.8 is 274.4. 274.4. And we can combine these two terms right here. They're just constants. So 274.4 and 245. So this can simplify even further to be FHY plus 0.5 FT minus 5 19.4. Okay, so that's about as far as we can get just looking at this equilibrium equation, summing the forces in the y direction. But now let's look at summing the forces in the x direction. In the x direction, we have this force and this force, the x components of the hinge force and the tension force. So they're going to cancel each other out, so their sum will be equal to 0. We're assuming that the hinge force is to the right, so we're saying that that's going to be a positive FHX, the hinge force in the x direction, positive to the right, minus FTX, the tension force in the x direction, and that's to the left, so we'll make that negative. That equals 0. Okay, so in other words, FHX is equal to FTX. Now, sometimes just using these two equations alone, we can use some type of method of solving a system of equations, maybe substitution method. But we've got different variables here. We've got FHX. There's no FHX up here. It's FHY. Then we've got FTX, and we just have FT up here. So I think we're going to need to explore our third equilibrium equation. So let's advance this slide. And let's sum the torque or moments about the hinge. Okay, so these forces that pass through the hinge, they don't cause any type of rotation or torque. You have to have some perpendicular distance away from the axis of rotation to cause a torque. So here we go. This one does. So let me write out the sum of torque is going to equal 0. And we have our 25 kilogram mass multiplied by 9.8 meters per second squared, changed from a mass into a force. And then we also have to multiply by its moment arm distance, how far from the hinge to that load. Well, the length of the beam overall is 2.2, so the center of mass or centroid of the beam is half that, so it's going to be 1.10 meters. So that's force times distance. That's the torque caused by the self-weight, and that's going to be in the clockwise direction, so we'll call that negative. And then we're going to, let's see what else. We have the weight of the sign out here on the end. That's also going to cause a negative moment. Negative 28.0 kilograms times 9.8 meters per second squared. And its moment arm distance is 2.20 meters. Okay, and what else? The only other force that is going to be perpendicular to the beam, which will cause a moment, is this FTY. It's going up, so it's going to cause rotation in the counterclockwise or positive direction. So I've got plus FTY times 2.2 meters. Now I have an equation that only has one unknown variable, so I can solve for it. So my FTY, I don't know why it does that there. At any rate, that's going to be equal to, let's see, 25 times 9.8 times 1.10 plus 28 times 9.8 times 2.20, all of that divided by 2.2. And that is equal to 396.9 Newton meters. And I'll have to pick this up in the next video.